we're going to start looking at rational functions and rational expressions. And things that get a little icky, but it's okay because we can do it. Yeah, I know it's an icky one. Did you say 36?
Yeah.
36 was not on homework 2. Oh, homework 3, sorry. Yeah, it is, sorry. It's icky. Yeah, it's icky.
The x1/3 and the y1/3, the second half is being multiplied together, right?
Uh-huh.
So we have to keep those together?
Just touch them next to, yep, just put them next to each other, and then eventually you'll combine like terms.
I'm trying to do this in the box. Because I can't.
You can, it'll just be tiny.
Yeah.
You might want to post a note for a bigger box. All right, well, we are going to start looking at section 1.4 here. So we've got fractional expressions, and we're going to deal with a rational expression. So fractional expression is a little bit more vague. It's just a quotient, so a fraction that has two expressions. A rational expression is more specific because it is a quotient of two polynomials. So a lot of times the phrases will be used almost interchangeably. They are slightly different, but barely. The only difference is that in the fractional expressions, we're not so picky about your powers. If you have negative exponents, that makes it a fractional expression because polynomials don't get negative exponents. Or roots, or things like that. So with our rational expressions, we wind up with some problems in our domain a little bit. Because what is the one thing we are not allowed to divide stuff by? 0. So if our denominator equals 0, we have a problem. So our domain, we're going to typically write on a lot of these. And just as a reminder, the definition for our domain are the x values that work in an expression. So we are going to wind up with something called a domain restriction when we have these fraction stuff, because we have that one thing we can't divide by. So our domain restriction is a rule that we have to state to make sure our denominator doesn't equal 0. So, and I know this is going to be right at the bottom, I'm sorry. So it's a rule stated, whether it's by us or by the book, to make sure the denominator is not equal to 0. I'm going to zoom it up just a little bit because I know for my people in the back this is a little difficult to see. There we go. So those are the pieces that I wrote in. So if we look at this little one right here, we've got x squared minus 4 over x plus 3. What value of x would make my denominator 0? Negative 3. So our restriction for this is typically going to say either x cannot equal negative 3. You could write it like that. Or we'll do it as an interval in our interval notation where it can be anything except negative 3. which means if we do it in interval notation, that would be from negative infinity to negative 3, and then from negative 3 to infinity with the parentheses because we cannot include it. I am 100% okay if we write it like this. We'll get into our interval notation more as we get later on in the chapter. We're going to use a whole bunch of interval notation later in the semester. So this is if we remember it, and if we don't, this is 100% okay. It means the same thing. This is just exclusive versus inclusive. Meaning we kick it out or we keep everybody else in. So this is 100% okay. And in fact, I will probably write it this way for today because this is a lot. Does anybody need more time on this page with these things? I try not to move too fast, especially after a quiz, because I know our brains are gooey. Especially on a Friday. Gooey. And I get that. All right, so what we're going to do now is we are going to try and do some simplifying. You have worked with these before. You did these in Algebra 2. We're going to try and simplify these. When we are simplifying fractions, I can eliminate things out that have the exact same piece, top and bottom. So when we're looking at expressions like this first one over here, where we have 2x plus 6 over 4x minus 12. Right off the bat, I don't see much we can do.
Don't they have a greatest common factor too?
Both pieces have greatest common factors. So since we have this addition and subtraction in here, I can't just kind of cross things out as it is. I know we're super tempted with the 6 and the 12 to make this be a 2 down here. That does not work. We can only cancel things out that have been multiplied together. So we have to get it into factored form before we can simplify. So that means we need to come here, or come through here, and do a little bit of factoring. So in our numerator up here, what do we have as a common factor, a greatest common factor between 2x and 6? 2. And that's going to leave us with our factor of x plus 3, right? What do we have as a greatest common factor on this bottom one, 4x minus 12? 4. Leaving us with just an x minus 3. Now do we have something we can simplify? Yeah, and the 2 and the 4. That'll simplify down to be what? 1 over 2. They're both divisible by 2. So we can write our simplified version of this as our fraction that has, in the numerator, we're just left with our x plus 3. When we only have one piece, we can drop our parentheses. And in our denominator, we're left with our 2 and the x minus 3. More often than not, we are going to leave our denominator in factored form. Numerators, hit and miss. We're going to switch back and forth. A lot of the time, our denominator is going to stay in factored form. It's just making your life more complicated to multiply out. So don't. Questions on the first one? I say we've done stuff like that before. It's just been a minute. Ooh. So let's look at the one on the right. A little more complicated. Now we've got two quadratics. Same kind of vibe though. I can't cancel things out when I have adding or subtracting up there. I can only cancel things out that have been multiplied together. So before I can try and simplify this, I need to factor both pieces. We need to factor our numerator, we need to factor our denominator. Luckily, both of these are shortcut ready because we have a values of 1. So when we look at our numerator up here, and we try and factor it, our a times c gives us 6, our b is negative 5. What pair of numbers multiplies to make 6 and adds to make negative 5? Negative 2 and negative 3 will multiply to make that positive 6. I heard a couple people talk about negative 6 and 1. Those will add up to be negative 5, but those would multiply to make a negative 6, not a positive 6. So be super careful on that. The 6 ones honestly come back and kick us in the teeth because we get a little overexcited sometimes. So be really, really careful, especially when we know multiple factors that have similar pieces. So you don't have to do the full box. You don't have to do the full process on this. We know that this is going to be the same thing as x minus 2 and x minus 3. Whenever our a value is 1, we don't necessarily need the full thing. If you want to do it, totally fine. Absolutely valid. Factor it however you want. We just need to factor. I don't necessarily care how we factor. So then let's do the same thing with our denominator. What are we going to get when we look at negative 15 as a positive 2? We're going to have a negative 3 and a positive 5. Negative 3 times 5 gives us that negative 15. Negative 3 plus 5 gives us that positive 2. So then we can get this in its factored form. That gives us our x minus 3 and our x plus 5. So whenever we have those a values of 1, it is 100% okay to take those shortcuts. Totally okay. What do we notice here? One of these pieces is canceling out. Which one's canceling out? The x minus 3 cancels out because it's exactly the same. I can only cancel out pieces that are exactly the same. That's why we couldn't cancel out the x plus 3 and the x minus 3 on the first one. So our answer here is going to be the pieces we're left with. I'm left with an x minus 2, and I'm left with an x plus 5. Okay. Questions on those two? Gonna say deep breaths.
Oh God.
We can do this. We can do this. They're a little bit bigger. It's been scrambled. It looks weird. But we can do this. It's factoring. We can do this with factoring by grouping. So I know it's gross. It's nasty. If you want to scooch things around and reorganize, totally fine. I'm going to kind of rock it as it is. Because we have 4 pieces anyway. So I'm going to factor this one with our grouping. I'm going to take my 2x plus 4 as a group and my minus x cubed minus 2x squared as a group. What do these 2 pieces have in common? 2. We have 2, and it's going to leave us with our x plus 2. What do these 2 pieces have in common? We're going to take out a minus x squared. When we do, if I take out minus x squared, it's going to leave me with an x. If I take minus x squared out of minus 2x squared, we're left with a plus 2. So this does factor out. We're going to wind up with, in our numerator here, our x plus 2, and our other factor is 2 plus minus x squared, or 2 minus x squared. That's our numerator. Let's put a little barrier for us here, just because that's where that was for that guy. Now we got to look at our denominator, and thank goodness it's something more familiar. X squared plus 5x plus 6. So this is just normal factoring, where my a times c gives me 6. My b is 5. What pair of numbers multiplies to make 6, adds to make 5? 2 and 3. 3 and 2, 2 and 3, either way. So we have our x plus 2 and our x plus 3. So it's just factoring. The x plus 2's cancel out. And we're left with our 2 minus x squared. If you want to switch that around to be minus x squared plus 2, totally fine. And our denominator has x plus 3. So this is our simplified expression. We're going to do one more, and then we'll talk about those domain restrictions on the ones we've just done, and then we'll be done for the day, because I know our brains are tired. So the one on the right here, it's y's, which we get a little nervous about, and things seem small, but these are things we talked about yesterday. Because our numerator is what? Difference of squares. Difference of squares. So that means I don't even need to write anything. What's my factored form? We're going to have plus 3 and minus 3. Be super careful, though, because our variable is actually y. Y plus 3 and y minus 3. Our bottom piece is what? Because this is the sum of cubes. So we have to use our SOAP pattern. Because we know that this thing is made up of y that's been cubed. And what cubed gives me 27? 3 cubed. Same thing, right? So this is when we use our other special pattern, where I have my front and the back. We use the same sign, so this side gets a plus. Then I get my first piece squared. Opposite sign with the product of y times 3, also known as 3y. Always plus the last bit squared. So the 3 squared. 9. So we have to factor them first. Whenever we have our sum or difference of cubes, we use that SOAP pattern from yesterday. So what do we notice down here? The y plus 3's cancel out. So this piece is going to cancel out with this piece. So our answer on this one, fully simplified, is going to be our y minus 3 over this quadratic looking thing. Y squared minus 3y plus 9. And you can look and see and try and see if that factors. It won't, as far as I'm aware, ever on a difference of cubes or sum of cubes, but you can always check. That's our simplified answer here. Questions on the simplifying part? Let's talk about the domain restrictions. We'll look over at these ones real quick. So these were our answers. I just didn't box them. So when we're looking to see what our denominators cannot be, we want to know what would make our denominator 0. So on this one, what value of x would make my denominator 0? 3. So our domain restriction on this one would say that x cannot equal 3. So that would be the domain restriction on this one. On this one, what will make our denominator 0? Negative 5. So x cannot equal negative 5. But we also have this guy in here when we put it in factored form. So if we had our original equation, if I put in 3, it would still give me a 0. So we have to include the ones that cancel out as well in our domain. So x cannot equal 3 either because of that guy. We are not going to have tons where we have to write these out, because especially like the quadratic one we had, gross, because we'd have to solve that one quadratic formula style. When we get into like more domain restriction and we're dealing with these as functions and OSE graphs, eventually, we'll work with them as we get closer to that. Okay? So we're going to keep working with these next week because there's a bunch of these. So when you're looking at homework 1-4, just know that they're going to get more complicated, and we're going to work several of them together. So please don't panic. Okay? It's not due till Wednesday. Have a great rest of your day. Have a great weekend. I will see you next week.